Welcome again to the Wolves and Moose of Isle Royale. In this lecture, we're going to focus on the mechanisms of predation, and it'll take us 2 lecture periods to do that. This will be the first part. And just to recall and to recap, up until now, one of the things that we've been doing has been analyzing the time series of abundances of wolves and moose for the past 5 decades. And we're going to take altogether 3 different approaches in doing so, and this lecture marks the beginning of this 3rd approach by looking at the mechanics, the very details of predation and what it is that Isle Royale shows us about all of that. And so before we can look at Isle Royale in any bit of detail, we have to cover just a little bit of theory about predation so that it all makes sense for us. And so we'll recap that really in just a few minutes, all the relevant theory that we need to have under our belt so that Isle Royale makes sense. But it begins with 2 fellows whose names are Lotka and Volterra. They did their work in the 1930s, and what they were responsible for in particular is developing this set of differential equations. 2 equations intended to describe predator and prey dynamics. The top equation, dx dt, is intended to describe the prey, and the bottom equation, dy dt, is intended to describe the predator. Now, these equations are what give us this, what you may know already about, is this characteristic cycling between predator and prey. Predator and prey cycles come from these equations. And so these equations are thought to have some validity, some appropriateness by various kinds of data that we've collected throughout the world. And one of the important pieces of data that's been around for some time is the very long time series of lynx and hare population cycles. Data for some populations exists for about 100 years or more. This would be one of those examples. This is about a 90-year time series. Snowshoe hare abundances fluctuating in black, lynx abundances fluctuating in the red dotted line, and they seem to cycle with some regularity. The peaks between, or the period of time between the peaks is about 10 years, and then it tends to be that the lynx peak follows the hare peak by about a year or 2, not in every case, but in most cases. And these are some of the patterns that are expected to arise from those equations that I just shown you. And so that these patterns occur in the real world has long been compelling. What we're going to do is we're going to not look at that kind of a big picture view, but we're going to deconstruct the details of these 2 equations. Now, the way these 2 equations are written right now, it's a little bit too abstract. It's written in about its most compact possible form right now, and while that's compact, it's not very easy to understand. And so what I'm going to do is I'm going to take these 2 equations and explain them to you in a little bit more of a narrative sort of a fashion. And so what we're looking at right now is the first equation. And the first equation has 3 parts. The first part is right here. It's the prey growth. It's on the left-hand side of the equation. That's what we're trying to predict. And the prey growth has basically 2 parts to it all. One part would be to say, well, what is the growth of the prey population in the absence of predation? And then from whatever that growth is, we'll subtract from that any losses due to predation. Losses due to predation can be described in a little bit more detail. It's the multiplication of 2 parts. One part would be to say, what is the kill rate? Remember, we've already talked quite a bit about the kill rate. It's the number of prey killed per predator per unit time. So it's that kill rate multiplied by the number of predators that were involved in that kill rate. And that gives you basically the total number of moose that were lost during that time frame. The second equation in these Lotka, Volterra, predator-prey equations, the second equation basically describes predator growth, and it can be described in various ways, but the simplest way to describe it is just to say that predator growth, what's here on the left-hand side of the equation, is simply some function of the kill rate. And the basic idea would be just, well, the greater the kill rate, in other words, the more food, well, the more growth that the predator population would experience. Okay, so when expressed in these kind of terms, these 2 equations aren't that difficult to understand. And there are 2 important lessons that we can derive from them straight away. The first is this appreciation for the kill rate. I've been emphasizing the kill rate a great deal already in the lectures, and now we see one of the reasons why. The kill rate is a term that shows up in both of these equations. Kill rate is the term that connects the two equations. If these two equations weren't connected, they'd just be doing their own thing. They wouldn't be interacting at all. And so again, it's the kill rate that connects them. As a result of these equations that were developed in the 1930s, it has become a research priority ever since then, for the last 80 years basically, to ask the question, well, because kill rate is so important, what determines kill rate? We know that kill rate is sometimes high and it's sometimes low. Why? What causes fluctuation in the kill rate? And when we talk about that, we sometimes have a special jargon term for it. It's referred to the functional response. It's maybe a little bit of a confusing term, a little bit vague, but for the moment, just associate the phrase functional response with an effort or an interest to understand kill rate and what causes it to fluctuate. The other lesson that we learn from this set of equations, the way that we're talking about them now, is that it becomes important to ask this relatively simple question: how does predator population growth respond to changes in the supply of prey or in the kill rate? In other words, basically it's just asking, what's the nature of that second equation? Is it a straight line? Is it a curved line? If it's a straight line, has it got a steep slope or a shallow slope? Basically, the second question refers to just what's the nature of that second equation. And when we speak about that second equation, sometimes it's referred to by also a special jargon term known as the numerical response. Okay, so those are the basics of predator-prey theory. It's those two equations. We need just a little bit more. Remember, I had mentioned to you that the functional response is a very important part of the whole thing. And the series of graphs that I'm going to show you now are about that functional response. The first idea that came across, and this was as early as in the 1930s, is this idea that as prey abundance increases, so would the kill rate. And the basic idea here is that, well, if you're a predator, well, the more prey there are, it'd be just easier to find them. And if it's easier to find them, you'll kill them more rapidly, and you'll get this relationship that we're looking at now. A straight line, kill rate increasing with prey abundance. But then there was another idea that said, well, maybe that's not so realistic, because at some point, prey would become so abundant that the predators, they would get full. They would get satiated. They would lose an interest to continue hunting at such a high rate because they had all the food that they needed. In this case, what would happen is that as prey abundance gets particularly high, well, then the kill rate would start to level off and give this kind of a shape. Then there's another idea that I won't go into the details of, but suggested that maybe the relationship between prey abundance and kill rate would look something like this. It would have this sigmoidal, or basically the sigmoidal type of shape. Each of these functional responses has a different name. They're referred to as type 1, type 2, and type 3, and they're characterized by those shapes: linear, asymptotic, and sigmoidal. Okay. Why would you, and I want to focus for the moment just on the type 1 and type 2 functional response. Why would you care to distinguish between those two? Sure, you could imagine that one is possible and maybe in the other one not so likely, or this sort of a thing. But what difference would it make? Well, these graphs that we're looking at, they can be expressed as equations, as functions. And those functions can be inserted into those predator-prey equations that we saw a few slides ago. A few slides ago, where we saw in those equations the words kill rate, you could replace those words with some function that represents either a straight line, like the type 1 functional response, or an asymptotic line, like the type 2 functional response. And here's the point. When you plug in a type 1 functional response, then what happens is that predation ends up being a pretty strong destabilizing force, especially with respect to the prey population. And the populations tend to cycle. Cycle in the ways that I showed you with those kind of abstract little kind of like sine waves, basically. And cycle in the same way that snowshoe hare and lynx appear to cycle. However, if you plug a type 2 functional response into those equations, then what happens is predation is not quite so destabilizing. What happens is that the system will start off exhibiting cycles, but those cycles eventually dampen off. And then what happens is eventually the predator abundance and the prey abundance become just two straight lines, two constant abundances for the predator and the prey. This all would occur as long as there was no external noise into the system. This would occur as long as those equations were describing everything that's going on. If there were maybe perturbations from, say, climate or disease or something like that, that would maybe cause those cycles to come back again, but then they would dampen out once again. And then a new perturbation might come along, another severe winter or ticks or something like that. That perturbation would cause the cycles to come back, but then they would dampen down again. The point is that predation has a stabilizing influence. And so that's why the nature of the functional response matters, because how the functional response is says something about what predation does to the prey population. All right? But that's all rather theoretical. I want to just be thinking about the Isle Royale, Wolf, and Moose time series while we ask that same question. Why would we care about the type 1 or type 2 functional response? And again, some kind of critical questions or statements here. We know that the population dynamics on Isle Royale are very, very dynamic, which is sometimes a special way of saying unstable. They fluctuate a great deal. Isn't that enough to kind of say, well, it must be that other option, that type 2 functional response? I'm sorry. It must be that type 1 functional response that's going on, because type 1 functional response is associated with destabilized population dynamics, associated with fluctuations, and that's what we see. Well, it doesn't have to be that way, because here's the thing, is that while we know that Isle Royale, Wolf, and Moose populations fluctuate, we don't know why they fluctuate. It could be that predation is the explanation. It could be that predation is the destabilizing force that causes those fluctuations. However, it could be some other factor. Maybe it's winter severity, or maybe it's something to do with the interaction between moose and their food supply. And so the reason to be focused and interested on the functional response is because we want to know why the populations fluctuate the way they do. Does predation have something to do with it? Okay, and so we're still thinking a little bit about the theory of predator and prey dynamics, and what we're really doing is I'm encapsulating for you about 70 years of theoretical development in just a few moments. And so everything that I described to you up until now, the type 1, 2, and 3 functional response, that was especially pertinent throughout the 1950s and 60s, and that was kind of not so many major developments in terms of thinking about functional response for a little while, until the 1990s, and then a new set of ideas come about. In those new set of ideas, they were appreciating this notion of what we can now call a prey-dependent functional response. It's called a prey-dependent functional response. It's the same thing we've been looking at so far, but we're going to give it a special label, call it prey-dependent, because the x-axis is prey abundance. Okay. In the 1990s, some people began to say, well, shouldn't the kill rate also depend on the number of predators? Well, why might that be? Well, a couple of reasons. One of the things is that sometimes predators compete with one another. And remember, we spoke in several lectures ago now, towards the beginning of the class, we spoke about interference competition between wolves, their territoriality. When wolves become more abundant, they spend more time defending their territories. If they spend more time defending their territories, then they'll probably spend less time on trying to find their next food item. They won't have the time to spend on it. And so that could maybe cause kill rates to go down. If that's true, then wouldn't the ratio of predator to prey capture that idea? You'll have to think about that a little bit on your own. How would, imagine if the prey is constant, but then you increase the number of predators, that will increase the ratio of predator to prey. If the predators are constant, but then the prey increases or decreases, then that would change the ratio accordingly. So in other words, you can kind of get both of these ideas together, fluctuations in prey, fluctuations in predator. We know they both might affect kill rate, or have good reasons to think they might affect kill rate. And this ratio is a good way to capture both of those ideas all at once. Okay? And so we can ask this question, how should more particularly the kill rate change as the ratio of predator to prey changes? And the idea is basically this. It's what's indicated in this graph here. Now, the graphs superficially look very similar. They both have these asymptotic shaped curves, okay? But But that similarity is deceiving, because the real important difference is that the x-axes of these graphs are different, and that ends up making all of the difference in the world. When these ideas were first being worked out, there was a little bit of controversy that came about because of it. And that controversy can be reflected a little bit by thinking about what a couple of pretty well-known ecologists said about them. A fellow whose last name is Slobodkin in the early 1990s, he said that ratio dependency represents this major clarifying step for the future of ecology. You know, it had been really 20 or 30 years since there had been any important developments in the nature of the functional response, and so Slobodkin thought this was a big deal. Peter Abrams, another very, very important, competent, valuable ecologist, makes a great deal of theoretical contributions into the field of ecology. He said that widespread acceptance of this idea would set predator-prey theory back by decades. And the reasons for their dispute is complicated. There are many, many different factors involved in it, but they include things like this. There's some very important philosophy of science for which these two people disagreed on, and their two views are very representative of a number of people. Perhaps during one of our discussion periods we can get into that philosophy of science, but for now, philosophy is a pretty important part about why these guys had such a disagreement. Another important reason is because there was another reason for the controversy is that for a long time there was absolutely no direct empirical evidence to help understand which of those two ideas would be better. And whenever you have an absence of evidence to tell you which is the better way, that's great for fueling controversy, because then all there is left to do is just to think your way through those things, and that part can be tricky and people can have different thoughts about what's going on. There's a third reason why there was controversy about these ideas, and it had to do with the implications. Depending on which of these functional responses you plug into those predator-to-prey equations, you get very different dynamics. If you believe in a type 2 prey-dependent functional response, like this guy here on the left, then what happens is that trophic cascades are very likely to occur in a food web. In other words, predators will exert this very strong and important influence on an entire ecosystem. When the predators increase, then that should cause the prey to decrease, and when the prey to decrease, that should cause vegetation to increase. That's basically what a trophic cascade is, and if you plug in a type 2 functional response that's prey dependent, that's typically what you'll get. However, by striking contrast, if you plug in a ratio dependent functional response into those predator-prey equations that Lotka and Volterra developed, then what happens is trophic cascades are very unlikely. Predators are a relatively unimportant part of the whole thing. The whole system basically becomes, instead of a top-down system, it becomes a bottom-up system. What happens is the amount of vegetation will fuel how many prey are available, and how many prey are available will determine how many predators are available. Predators are just along for the ride. You can't have two more different views on what an ecosystem might be like. And so for these reasons, for these three reasons that I mentioned, some philosophy of science, lack of direct evidence to help guide us, and then the stark differences in of the consequences of these two functional responses, those things all together made for this to be really quite a cantankerous debate in ecology throughout the 1990s. Okay, well, what does Isle Royale tell us about it all? Again, let me emphasize, until just about 10 years ago, there was no data to really tell us one way or the other what was going on. But we had been collecting all along, we had been collecting long before this question even became important, the data necessary to help answer this question. And so basically, what we need to know is, well, what we need to do is construct two graphs, and those graphs are indicated by what we have here. On this left graph, well, we want moose abundance on the x-axis and kill rate on the y-axis. On this other graph, we want the number of moose per wolf, and then it'll be kill rate is over here, still going to be reading the y-axis on the right-hand graph. Okay, so we need data to fill that out. Well, we've already talked about this before, but just to remind ourselves, it's the kill rate data that becomes so important. Every year for the last 40 years, we estimate what the kill rate is for the population. This graph here just to remind us how that was done. And so what happens is that for every year that we do this, we can get one data point that can go on each graph. One data point to say that for some particular year, the kill rate was approximately 1.2 kills per wolf per month. And for that same particular year, moose abundance was about 1,200, and the ratio of wolves to moose was a little over 50. Okay? So one entire year of effort to get those two data points. Well, anyways, if you do it for a long time, you get these graphs. And here's the thing. If we look at the graph on the left-hand side, what we see is that the R-squared is 37%. Of all of the fluctuations that we see in kill rate, 37% of that variation can be explained by moose abundance. And then the graph on the right-hand side, again, for all the variation that we can see in kill rate, 58% of that variation is explained by fluctuations in the number of moose per wolf from year to year. And so if you're fixated on this debate about which is better, well then it's pretty convincing, pretty straightforward that that ratio-dependent function response is the better way to go. But it turns out that there's more to it. The first thing that might come to your mind is that if you're not so fixated on the debate, if you're just interested a little bit more broadly, a little bit more generally in kill rates, you might ask this question, well, the ratio explains about 60% of the variation. What about the other 40% of the variation? In other words, what I mean to say is that very few of the data points fall right on that line. And so, for example, this data point right here, why is it higher than expected? What was going on that year to explain what's going on there? And just to pick another data point, this one right here, why was it lower? What else was going on? Was there something about the climate that was different that year? Was there something about the age structure of the prey population? What was it? And so with some of the Isle Royale data, we can explore some of those questions. Well, one of the things that's important and special about wolves is that they're social predators. They live in social groups. And that social structure can have an impact on their kill rates. And the best way to see that is to just assess rather directly what is the relationship between pack size and kill rate. And so that's what we have here on this graph. Pack size is along the x-axis. Each data point is for a different pack on Isle Royale during a different year. We've mentioned this already before. Look at how variable pack size is. It runs quite a range of values, from just lone individual wolves all the way up to 18 wolves being the biggest that we've observed on Isle Royale. And what we see is that about 30% of the fluctuations that we see in kill rate can be explained by fluctuations in pack size. Okay, so that adds a little bit more insight to what's going on. But think about that graph just a little bit. There's something a little funny going on there in the sense that if you live in a bigger pack, you get less food. I think I mentioned this just several lectures ago, but to remind ourselves, that's a little bit confusing because it seems as though, well, if you're in a bigger pack, you get less food. Wouldn't you be better off in a small pack where each wolf gets more food? Just because of the way they hunt, apparently. It seems as though they're killing more often on a per-wolf basis when they're in a smaller pack. Why wouldn't a big pack just split up into two small packs and they'd all do better off? Well, the reason is because the y-axis that we're looking at, it doesn't measure what the wolves eat, it measures what they kill. And those aren't always the same thing because of scavengers. And we'll spend a little bit more time focusing on this in a subsequent lecture, but for now, we can just be aware of the fact that what wolves kill is not always what they eat. If it's in a small pack, it takes those wolves a long time to eat the prey. If it takes them a long time to eat the prey, that's a lot of time for them to lose food to the scavengers. And what happens is that if you account for the different rates of loss to scavengers that occur for different pack sizes, the idea that a small pack would lose more food than a big pack because of how quickly they're eating the food, then what happens is that while the red line represents what they kill, and it would represent what they eat if there was no scavenging, but there is scavenging, and so when you account for that, the green line describes how much food they get to eat. And now we see that it's slightly better to be in a bigger pack than in a small pack. Not only that, that green line is pretty flat for a wide range, suggesting that the difference in food intake for a pack of, say, size 5 versus a pack of, say, size 18, it's not that different, which means that it's fine to be in a big pack or a small pack. It doesn't much matter. But anyways, to focus back on the main point, the social structure of wolves has an effect on the nature of the kill rate, which means the social structure of wolves will have an effect on the nature of predation overall. Okay, there's more. It's long been appreciated that winter severity seems like it should affect kill rate. It just seems that when field biologists are collecting their field data, performing necropsies in the wintertime, they just have this appreciation by what they can see with their eyes that, wow, when the snow is really deep and there's thick crust, these wolves really seem to be killing a lot of prey. You know, that had been just kind of a general idea from really several or many decades, but it hadn't been really demonstrated very, very carefully until kind of recently. And this graph shows the effect of that. And so what we have on the x-axis is winter severity. Winter severity is essentially being indexed by the North Atlantic Oscillation. It's transformed a little bit. That's why if you're familiar with NAO indices, you know that sometimes it's positive and sometimes negative, the index. It's been transformed here to be always positive. That's for some statistical reasons. But the most important point is that when the winters are severe, kill rates tend to be a little bit higher, and when the winters are mild, the kill rates tend to be a little bit lower. But probably what's most important is that even though wolf biologists have kind of appreciated for a very long time, winter must be important, one of the things that we know is that R squared value, it's not very high. Winter severity, fluctuations in the severity of winter from one year to the next, they indeed explain some of the fluctuations in kill rate, but not really all that many, not all that much. The age structure of prey is something that has long believed to have been important for understanding whether kill rates will be high or low in a particular year. And the basic idea is this, is that a moose population, the moose that are in that population, they're not all the same. They come, if you like, rather in three basic kinds. There are calves, there are prime-aged animals, which are basically between the ages of 2 and 9. And then there are older animals, older than about the age of 9. Those older animals are senescent. They tend to be more vulnerable to predation. And then, of course, the calves are more vulnerable to predation. And so it's been just generally appreciated, but not really demonstrated, that, well, maybe as the age structure fluctuates over time, maybe that affects the kill rates. In other words, maybe in some years when there's lots of, we'll just say, for example, calves, in years with lots of calves, maybe then the kill rate will be relatively high because calves are relatively easy to kill. An important idea. It had been around for a long time, but it hadn't ever really been assessed. Now, Royale gives a pretty important view on all of that, and here's the result of it, is that this, on the x-axis, is the frequency of calves in the diet. So over here would be when calves don't comprise any of the diet of wolves, any of the moose that the wolves are killing. And over here on this end, this is about 60-65% of the moose that wolves are killing end up being calves. That's what the right-hand side of this x-axis refers to. And then what we see here is that, not surprisingly, when calves are more common, that kill rate tends to increase. And the R-squared value, it's about 0.29. It's quite a bit more important, for example, than winter severity. Okay. Well, this is the view that we get when we look at each of these factors one at a time. When we look at predator-to-prey ratio, calf abundance, winter severity, social structure, when we look at them one at a time, you get the view that I just suggested. But there's a statistically more appropriate way, which is to basically kind of look at them all together to see what happens. And when we ask, this is basically another multiple regression technique, when we do that, we can display the result of that multiple regression technique in this way. We can think of a pie chart, and the pie chart represents all of the variation that we see in kill rates, and then we can say, okay, of all of that variation, what portion of it can be attributed to the various predictors? And so here we see that about 23% of the variation in kill rate can be attributed to moose. About 28% of the variation can be attributed to fluctuations in pack size from one year to the next. About 11% can be attributed to calves in the diet. By the time that you get those three factors in there, it turns out winter severity, there's nothing left for winter severity to explain or predict. It's kind of captured by all that other stuff. And then in the end, there end up being about 38% of the variation is unexplained. We don't know what causes it. So that ends up being one of our very best guesses. Okay. Altogether, it explains about 62% of the variation in kill rate. But it turns out there's another regression model that's pretty important to compare it to, and it would be this one here. It would be not a multiple regression model, but just a simple regression model, and it's actually one that we've already seen. We've already seen a graph of this, but now we see the pie chart. And the pie chart just shows us that for all of the variation that we see in kill rates, about 60% of it is explained by the ratio of moose to wolves. The portion explained here is very, very similar to the amount of variation explained by all of this. And so here's the question. On the one hand, we have a model that seems more realistic, and what I mean by that is it seems more realistic because everything we know about ecology tells us that processes like kill rate, they're not influenced by just one thing. Processes like kill rate, they're influenced by many things, all working together. And this model on the left-hand side suggests exactly that and gives us an image, a sense of, well, if they're all working together, which are the most important ones and which are the lesser important ones. However, there's another idea. It's very important to the philosophy of science. It's very important to kind of the theory about how can you be so sure you understand that this model is correct and this one is not so correct. And it's the idea of parsimony. The idea of parsimony basically says this. If you have two models that explain a similar amount of variation, like this explains a large portion of variation, this explains a similar portion of variation, so these two models are similar in that way, but the model on the right can explain that variation with just one predictor variable, and the one on the right, it takes 4 predictor variables, really 3 if you don't think about winter severity. This one takes 3, the other one takes 1. Isn't the model that can do the job with fewer variables, isn't that the better one? That's what the idea of parsimony says, and there's great weight given to parsimony, but in this particular case, it leads us to some confusion. And really what it does is it begs us to ask the question, what's the purpose of the model? If the purpose of the model is simply to make a good prediction, then this more parsimonious model is going to basically be the better way to go. And there's some kind of complicated statistical reasons for why that's true. But again, the basic idea, because it's important, I'll repeat it again, is that if your only goal is to make a prediction, then go with the parsimonious model. There's great evidence to suggest that that's the way to go. Evidence that I'm not going to show you now. However, if your goal is not so much to predict the future, but instead your goal is to just, I kind of want to understand how it works, then parsimony might not always be the best way to go. But then it becomes really difficult to figure out, well, which is the best way to go. And I'll leave this topic just at this spot for now, and if it's something that's of interest to students in the class, we can talk more about it during one of our discussion periods. Okay. So we've just talked about the functional response. And now what I want to do is I want to go back to these Lanka-Volterra predator-prey equations and remind us that there were 2 important questions that arose by thinking about these equations. One was the functional response, which is to ask what causes the kill rate to fluctuate. We've just been talking about that. The other question is about this numerical response, which is to ask the question, how do fluctuations in the kill rate, how do they translate into predator dynamics? How do they translate into fluctuations in abundance for the predator population? Again, this is the business of the numerical response. And there's been a pretty long-standing, simple, straightforward idea for what the numerical response should look like. It's believed that it should look like what's being shown on this graph here. And the basic idea is that as kill rate increases, well, the growth rate of the prey population should increase too, and it should increase at first linearly, but as the kill rate continues to increase, that growth rate should level off, should asymptote. And just to kind of help you out, what does this dotted line refer to? The dotted line just refers to the fact that growth rate for a predator population involves positive values. They would be these values up here, and negative values, these would be values down here, and then 0 divides the 2 regions. If the growth is up in this region here, the population is growing. If the growth is down in here, the population is shrinking. That's what this graph is describing. And so the basic idea is that, well, of course, when the kill rate is low, Well, if it's really quite low, well, the population should be shrinking. And in fact, if it's low but then continues to go lower, the population would not only shrink, but the population would shrink at even increasing rates as the food continued to dwindle. Okay, well, eventually you get enough food. Well, this graph would say, well, how much food? Well, by the time you got this much food and more, well, then you'll start to increase. Well, the wolf population can only grow so fast. It can only produce puppies so fast, and the animals are always going to die at some rate. They're just going to get old no matter how much food you get them. So you can just keep giving them more and more food, but eventually the growth rate is not going to increase anymore. That's what this graph describes. Okay? And it's presumed to be the essence of predation, it's assumed to be the essence of population dynamics for a predator. Okay. Those are just ideas, though. I mean, they're very reasonable ideas, but where's the evidence from nature to help us understand if this is a good idea or not? Well, there's some evidence that comes from predatory and parasitic arthropods, okay, mostly insects. And that work had been done in the 1970s, and it suggested that these ideas seemed to be true. But it had never been examined in a vertebrate predator. Excuse me for that. What a fundamental and basic idea. This idea that the more food you get, the more the predator population should go. It's a really simple idea. It's never really been evaluated in a vertebrate population of predators. Not for the entire time that this idea has been around, which has been now about 80 years. And to get an empirical sense for this data is pretty important because there are important conservation implications for this idea. And wolves are a great illustration of those implications. The implication is basically this, and I'm oversimplifying on purpose to make the point easy to understand. The basic idea behind predator conservation, the basic idea behind wolf conservation, is that wolves need two things. Wolves need to not be shot by humans, and they need a good food supply. Usually some kind of ungulate, elk or moose or whatever the case may be. And if you give them those two things, protection from people shooting them, and give them a good food supply, they should do just fine. Well, that idea comes from this idea of the numerical response. So it's not until about the year 2004 that this idea is assessed in wolves for the first time, or actually for that matter for any vertebrate predator population. And so again, the data that we're going to be looking at is on the x-axis is going to be kill rate, that same very important statistic that we've been measuring for 4 decades. And then on this axis is going to be the wolf growth rate. Now we've got numbers on this axis, so this is the 0 growth rate line. These are growing populations. If the population is up here, this is shrinking. Some of these numbers are very big. Just to give you some context, that would be growing at a rate of 40% per year. Just to use easy numbers, if you had 100 wolves, then the very next year you'd have 140 wolves. 40% growth is what that means. And then this would be, 40% decline from one year to the next. That's what those numbers mean. And when you take the data from Isle Royale, 4 decades worth, this is the answer you get. And again, this depends on whether you view this from the I'm a glass half empty kind of person, or I'm a glass is half full kind of person. If you're I'm a glass is half full kind of person, then would you look at this and say, oh, we get some really interesting confirmation of a basic theory that we've had for a long time, which is indeed as the kill rate increases, so does the wolf population growth rate. And we can go a little bit further and say not only that, but it explains an interesting and important amount of the variation that we see. About 20% of the variation that we see in 20% of the variation that we see in the wolf population growth rate can be explained by the amount of food that they're getting. It's all very good. If you're a little bit glass half empty kind of person, then what you should be impressed with, of course, is what about the other 81% of the variation? The overwhelming majority of fluctuations in the wolf population dynamics are not explained by food. And of course, it begs the question, well, what is it? On Isle Royale, one of the very important things is something known as demographic stochasticity, which are these kind of random fluctuations that really don't have any population dynamical explanation. They're just random chance events. A wolf dies here, extra couple of wolves are born just by luck here, or maybe not so many in a particular year. Those chance events are not very important when a population is big, but when a population is small, like on Isle Royale, a couple of dozen wolves, those chance events can be a big deal. A lot of the fluctuations we see in Isle Royale wolves are attributed to that. Disease is another thing. We know that disease played a large role in some of those big population declines for the wolves. But there are questions about maybe are there other years for which disease also played a role, maybe not so dramatically, but enough to explain some of this variation. We don't have the good answers to that. But of course it has important implications for other predator populations, which is, well, maybe they need more than just not being shot by humans and a good food supply. There might be more that they need than just that. Okay. So let's compare now in a kind of a schematic sense. How does the theory compare with the real world? So this is the theory, those two equations connected by the kill rate. Okay? Well, what does the real world say? The real world says, well, that functional response, that kill rate, this thing here and this thing here, if we want to explain those, well, we can explain about 60% of the variation in that from the functional response. And then that numerical response, we don't do quite as well there. We only explain about 20% of the variation. Maybe you've already guessed by now, but I'm a glass is half empty kind of guy. Not just to be pessimistic for the sake of being pessimistic, but I always want to know more. I always want to know, okay, if that's 60% and 20% of the variation, where's the rest? What explains the rest of the variation? We can always do better if we think hard about it, if we collect more data and that sort of thing. So how can we do a better job? Well, this is how we can do a better job. It starts by making some modifications to this theory. It turns out that there's something really important missing from this theory that's been with us for so many years. And what is it? Well, we can start to think of it in this way. Predation has two perspectives. One perspective is how it is that killing moose affects the wolves. That's through the kill rate. But the other perspective is to say how it is that wolves killing moose, how does that affect the moose population? That's the other perspective. And so there are two sides to the same coin, if you like. One side is to say that predation represents a source of food for the wolves, and the other side of the coin is to say that it's a source of mortality for the moose. And the best way to be thinking about food for wolves is the kill rate. Kill rate is the wolves' perspective on predation, and that's what we've been focusing on. And so what predation theory for the past 80 years or so has basically been not doing a very good job on the other side, which it turns out is best represented by a different statistic, a statistic that we've known about but just haven't paid much attention to for a very long time. It's called the predation rate. The predation rate is the moose's perspective on predation. The predation rate is the best way to see how it is that predation represents a source of mortality for the moose. And so we need to account for both of these ideas essentially at the same time. Now the kill rate we've been talking about a lot already, so we know a lot about it. It's a statistic. It's measured by a certain units, and those units are the number of kills per wolf per day, or maybe per month, whatever time unit we like is fine. The predation rate is something a little bit different though. The predation rate is indicated by this equation right here. It's a ratio between two numbers. It's the number of wolf-killed moose that occurred during a particular year, divided by the total number of moose that existed in the population that year. So in other words, it's the proportion of moose that are killed by wolves in a particular year. Okay. And so what we can do is we can go back to this traditional set of equations for predation theory, and we can ask ourselves, where is the predation rate in this equation? If you look at it superficially, it's not there. And you'd say, well, the fact that it's missing might be part of the problem. Well, okay, this is a pretty critical view, and as somebody who wanted to defend this traditional theory, what they would say is this. Is they would say, well, you can see, can't you, that the predation rate really is just some function of the kill rate. A little bit more precisely, if you know what the kill rate is, and if you know how many predators there are, and if you know how many prey there are, and if you take the kill rate and multiply it by the predation rate and divide that product by the number of prey, then you have the predation rate. You can, if you like, work through that algebra on your own to demonstrate to yourself that that's true. You can do that by following the units, just using unit cancellation. If you don't want to do that, that's fine. You can just take my word for it here. And again, the thing to understand is that if you know these three things, then you know the predation rate. Well, if you know predator growth and if you know prey growth, well, then you know how many predators and prey there are. And if you know the kill rate, because that's part of the model, well, then you should know these things already. And so what a person who wanted to defend these equations would say is that the predation rate, it's implicit, it's implied in there. It's kind of hidden, it's there, don't worry about it, it's all right. However, the trouble is that for that to be a reasonable perspective, you would expect that the kill rate and the predation rate will be correlated. Then, with this idea that if you knew one, the other one should be kind of coming along the ride for it. There's different units for sure, different numbers attached to those two statistics, but when one goes up, the other one should go up too, right? Well, okay. And we expect some relationship like this, where, of course, on the x-axis you have kill rate, on the y-axis is predation rate. Now we're seeing predation rate on a graph for the first time, so let me just draw attention to those actual values. 0.1, that means that a predation rate of 0.1 means that in a particular year, the wolf population will be killing 10% of the moose population. If it were very, very high, then the wolves would be killing 30% of the moose in a particular year. That's how to read the numbers on the y-axis. And again, we expect them to be correlated by this kind of traditional theory, but we don't have to just take this for granted. We don't have to think our way through this and believe it. We can ask this question of the data from Isle Royale, and this is a finding that wasn't appreciated until just about the year 2010. And what we realized from Isle Royale is the first thing is that there is a tendency for as kill rate to increase, for the predation rate to go down in this way here. That's very unexpected. The other thing is that, and the more important thing, is that variation in kill rate says very little about the variation in the predation rate. The R-squared is very low. So knowing about the kill rate tells you very little about the predation rate. Okay? So what the lesson is that we have to take these two perspectives into account separately. We have to treat them each with their own kind of emphasis and focus. We've already focused on the kill rate, and we've asked ourselves, well, what causes the kill rate to fluctuate? And we learned some things. The ratio of wolves to moose, winter severity, pack size, age structure in the prey, those are all important causes in the fluctuation of kill rate. And then we asked ourselves, what are the consequences of the kill rate? Well, we say, well, it explains some of the growth in the wolf population. We have to do the same thing for predation rate. We have to say, well, what are its causes and what are its consequences? And so we can ask a familiar question, which is to say, well, is it wolves that cause fluctuation in predation rate? Or is it fluctuations from one year to the next in climate that cause fluctuations in predation rate? Could even possibly fluctuations in the abundance of food explain fluctuations in predation rate? Well, how would that work? Well, if there's not much food, maybe it will weaken all of the moose. If the moose are weakened, it's easier to kill them, and then the predation rate goes up. That's a possibility anyways. It's something we might want to check out. And then we can ask, what are the consequences of predation rate sometimes being low and sometimes being high, which is another way of saying, how does the predation rate affect moose population dynamics, or how does it affect the growth rate in the moose population? That's what we want to focus on for this next set of slides. And so, before we look at data from Isle Royale, what we need to do is just look at some theoretical possibilities, because these theoretical possibilities will help orient us when we see the real data. Okay, first of all, just a blank graph to help us understand some things. On this graph, on the x-axis will be predation rate. It will be going from low numbers to high numbers. On the y-axis is the prey population growth rate. That's the percent growth that the prey population will exhibit from one year to the next. Right across the middle here would be zero growth. These would be positive numbers. These would be negative numbers. And one possibility is something referred to as compensatory predation. Compensatory predation basically says this, that as the predation rate increases, there is no effect on the prey population growth rate. The prey population growth rate in a typical year is some positive number, or maybe some number close to zero, and it's basically unaffected by the predation rate. Why is this called compensatory growth rate? It's called this because the idea behind it, the ecology behind this idea, is that, well, what it is that wolves kill are moose that are going to die anyways. The fact that the wolves kill them doesn't matter at all. The wolves are killing, the hypothesis says, the wolves are killing weakened moose, old moose that are going to die anyways, calves that wouldn't have survived anyways. And because they're killing those kinds of animals, it's not affecting the growth rate, because the growth rate is being affected by other stuff. This is the wolves are scavengers, but they don't quite wait for the moose to die. That's what that idea is. The opposite idea is the notion of additive predation. It basically says that for every 1% increase in the predation rate, there will be a 1% decrease in the prey population growth rate. It'll be a negative slope, and the value of that slope will be -1, or maybe more precisely, -1%. And the thing that's important here is that in some important way, the units of this x and y axis are the same. This is expressed as a percentage growth rate, and this is expressed as a percentage of the population that was killed. So there's a parity between the x and y axis that's pretty useful. And then there's an intermediate possibility where there's a partial compensation, or partial additivity, if you like. And the idea here is that, yes, indeed, as the predation rate increases, there is a decline in the growth rate, but it's not a one-for-one sort of a decline. In other words, the slope is negative, but it's not so steep as -1. Maybe it's -0.5, or maybe it's -0.25. And so you can quantify rather precisely how close you are to this situation or how close you are to this situation by just asking yourself, what is the value of the slope, when we get to look at the real data. And then there's this kind of mixed effect sort of a thing, which would basically say for maybe low levels of predation, there's no effect at all on the growth rate. But then as predation rate continues to increase, the effect becomes increasingly steep. And then you get basically this nonlinear shape. This is just well, it's basically just a mixture of this idea and this idea together. And so when we look at the real data, we can ask which one of these theoretical possibilities does the real data look like. And here comes the real data from Isle Royale. Again, predation rate on the x-axis going all the way up to 30%. Moose growth rate on the y-axis at its very lowest rate, -40%. At its very highest rates, 20% in the positive. And here's what we get from the Isle Royale data, is we very, very clearly get a negative slope. There's no doubt about that. The R-squared is not so bad. Of all of the things that could possibly affect a moose population, weather, food, age structure, the fact that, hey, you just got a lot of old moose in the moose population right now, they don't reproduce as much and they die at kind of a high rate just because they're old, that can affect the growth rate of a moose population as well. Of all of those things that can affect the moose population growth rate, R-squared is 66. Being assigned to one predictor variable, the predation rate, that's pretty good. Moreover, look at that slope. The slope is very negative, -1.7. That means for every 1% increase in predation rate, the moose population growth rate will be declined by almost 2%. That's more than additive. You might call it super additive. And it's a little hard to know how to interpret that. It could be things like, and again, I want to emphasize, we really don't know. So these are just speculation. One possibility is that when wolves kill prey, and if what they happen to kill, for example, is a pregnant cow, that might be like double duty. That might have a big, big impact. And so that can explain maybe that very, very steep line. Another possibility is not nearly as interesting, but it's just as real, is that when we make graphs like this, there's what's referred to as measurement error. And again, what you can think of, if you like, is that there is some true underlying relationship between predation rate and moose growth rate. It's this true relationship that's out there, and we have to go assess it. And we assess it by gathering this data, but the data has noise in it. It has basically measurement error. This data point is an estimate. It's not the actual value for a particular year. It's just our best estimate for that value, our best estimate for predation rate, our best estimate for moose growth rate. What if that data point really is, belongs right up here? And what if this data point really belongs somewhere over here? Each one of these data points, if you like, is jiggled a little bit from its true location that we just don't know what it's at. And that jiggling might possibly explain why this is so steep. Maybe the slope isn't really quite that steep. Even if it's not that steep, this number, -1.7, is certainly much closer to -1 than it is to 0. And so if we go back to this example, Isle Royale seems to suggest that life is a lot more like this It's a lot more like this than it is any of the other cases. Okay. But what I want to emphasize right now is that this graph is a pattern. It's just an observation. And from that pattern, we would like to infer or make conclusions about the process that underlies that pattern. And so another way to say that is we want to ask the question, is predation actually the cause of what's going on there? Or is there something else going on and these two things are just correlated? Not a causal relationship, just a correlative relationship. In order to understand this, we need to distinguish a little bit better between pattern and process. And with the Isle Royale data, we can do that. And here's how. Again, and I want to illustrate this through a series of basically graphical cartoons to kind of help us wrap our minds around the idea at first, then we'll look at the real data. Here's the pattern. As predation rate increases, prey growth rate declines. One possibility is that the process that underlies that pattern is indeed a top-down process. And all I mean to indicate here is that yes, indeed, the increasing predation rate causes, that red arrow I mean to symbolize causes, a causal relationship. The increasing predation rate causes the prey population to decline. It's a straightforward possibility, and that's just fine. But there's another possibility. And that possibility is that this pattern right here, the process that underlies it is a set of abiotic processes. And it might look something like this, is that it is severe winters that's driving the whole thing. And a severe winter might do two things. The first thing that it might do is cause the prey population to decline in growth rate. Severe winter, population doesn't do as well, the growth rate declines. And along with that, well, why is the prey population declining? Well, because the moose aren't doing so well, because it's a severe winter. Well, if the moose aren't doing so well, well, the wolves will maybe benefit from that. The predation rate will go up, but that's just a side effect, if you will. It's really the severe winter that's causing that predation rate to go up. Wolves are just what it's being manifest through. And so the question for us is, which of these two processes underlies that pattern? Okay, well, there's one more pattern that we can look at that will help us tell the difference between these two processes. Here's the one pattern. We can ask of the Isle Royale data, what is the relationship between wolf density or abundance? How is that related to predation rate? You know, the basic idea might be, well, that as wolf density increases, well, then the predation rate would increase. If that's true, well, then we would think that this is a top-down process. We'd think that, you know, basically this side of the graph is what's going on. However, what if we look at another relationship, the relationship between winter severity and predation rate? And what if we find there's a strong relationship there? In the severe winters, there's a really high predation rate. Well, if that's the case, well, then that would suggest to us that, you know, basically this is the process that's going on. And so the question for us is, which of these two processes is stronger? Here's all the data. This graph we've already seen. We saw this several slides ago. It's the one that shows that as predation rate increases, the prey growth rate declines, and it declines quite steeply. This is the relationship between wolf density and predation rate. This is the line right here. It goes up as we would have expected. Here's what's really important about it is that the R-squared value is almost 50%. The p-value is very, very small, suggesting that it's a highly significant relationship. This is the relationship over here between winter severity and predation rate. As the winters become more severe, I'm sorry, one thing is that this scale is a bit reversed. The severe winters are over here on the left by this index that I'm using, and the mild winters are over here on the right. And so what happens is that when the winters are severe, the predation rate is a little bit high, but it doesn't explain a great deal of the variation. The variation explained is only about 13%. And so what happens is that while it is fair to say that both processes are occurring at the same time, it is definitely the case that the top-down process is the stronger one. So when we ask this question, what causes the predation rate to fluctuate from one year to the next, we can say the answer is wolf abundance. And we can ask, what is the consequence of that? Well, I should move on to the next slide here. We've already, several slides ago now, talked about the causes and consequences of kill rate, and I said that we would next look at the causes and consequences of predation rate, and now we can say, well, the cause of fluctuation in predation rate is mostly attributable to wolves, and the consequences of that predation rate is a pretty striking, very clear tendency for the moose population to decline when the predation rates are high. Okay. Last couple of slides now to just kind of wrap things up here for this first part of looking at the mechanics of predation. I want to remind you of the traditional view, the view that's been with us for about 80 years. And that traditional view says that predation has three parts to it. One part is to know what the prey abundance is, one part is to know what the predator abundance is, and one part is to understand the nature of the kill rate. And it basically says that, well, the functional response is a way of saying that prey abundance and predator abundance both influence what the kill rate is. And then the numerical response says that, well, once you know what the kill rate is, then that feeds into the predator population, tells us how many predators there are going to be in the upcoming year, and that's it. That's all there is. Just three parts and two basic relationships. And this links the predator and prey population, and you get some pretty complicated dynamics when that happens, and you can explain some things that occur in the real world when you think of it that way. Oh, I should point out one more thing, too. And then what's also definitely implied and accounted for by this traditional theory is that the kill rate also can be used to kind of algebraically tell you how many prey have been removed from the prey population. This closes the circle, and then this is that traditional view. And of course, one of the things that's assumed is that the predation rate, PR, is that the predation rate can be predicted rather simply from the kill rate, the predator abundance, and the prey abundance. So all of that is captured by the traditional view. Of course, Royale illustrates really for the first time, and only recently, that there's problems with that idea. And the problem is that the kill rate and predation rate actually aren't correlated hardly at all. And that makes this idea pretty weak. The conventional idea starts with the old idea. The new view. The new view on predation theory starts with the old view. It starts with the old view by saying that yes, indeed, the kill rate is important, prey abundance is important, predator abundance is important. Yes, indeed, it's the predator abundance and the prey abundance that determine the functional that represent the functional response, determining the kill rate. Yes, once you know the kill rate, it tells you something about what predator abundance is going to be, but there's more. And what's more is just you have to treat the predation rate as its own separate idea. You have to ask, okay, what causes the predation rate to fluctuate over time? And what we realize is that three things affect predation rate. It takes a prey abundance, predator abundance, and kill rate. All three of these determine how it is that the predation rate is going to fluctuate. And once you know what the predation rate is, this is the best way to understand how prey abundance is going to change. And then it turns out there's more. And this is the more that we really haven't talked about too much. Well, no, I take that back. We talked about it earlier in this lecture. If you want to know more about what affects the kill rate, not only do you need to know how many predators there are, but you need to know you need to know things about the predators that are different from their abundance, like pack size, their social structure. What I haven't shown you here, but evidence that comes from Yellowstone National Park, where wolves are studied pretty intensively there, it turns out that the age of the wolves that are involved in making those kills has an effect on what the kill rate's going to be. When wolves get a little bit too old, they end up not being quite as good at killing prey. And so if you have a very old population, the kill rate may not be as high. So age structure of the predator population also matters. We learned that from Yellowstone. The level of skill. Oops, I changed my thing here. Hold on. Here, hold on one second. We will do this, and we will do this, and this. All right, now I think I've got it. Also, the skill of the wolves matters in affecting the kill rate. What it basically comes down to is that, like people, not all wolves are the same. Some wolves are better than others. Some wolves are better than others at killing prey. And it turns out you can kind of measure those differences, and that affects the kill rate as well. And the other thing that we know is that the abundance of prey is not all that matters as well. It's not just the number of prey that are on the landscape that are going to help determine what the kill rate is going to be and help determine what the predation rate is going to be, but also the condition and health of those prey are also going to matter. What's the age structure of the prey population? Are the prey population weakened by a severe winter? That matters as well. And then, of course, not only do those things, the condition of the prey, affect the kill rates, but the condition of the prey are also going to affect, the relationship with predation rates. Again, whether those moose are in healthy condition or not. Healthy because of maybe the age structure or because of the winter severity. Well, one final thing is that in all of this we haven't considered too carefully how it is, only mentioned it casually, how it is that climatic variables might enter onto all of this. Here's the main point. Every one of these arrows represents an additional level of complexity. All of them. The blue ones, the red ones, the green ones, the pink ones. That's an awful lot of arrows compared to this old traditional view. And so if we are wondering why it is that predation dynamics are so complicated and why it's hard to predict what's going to happen next in a place like Isle Royale, even though we measure so many things and so carefully and for so long, the reason that it's hard to predict that stuff is because, well, it's all interacting in a pretty complicated way. We shouldn't be surprised when we're unable to predict it. And so what happens is that and this speaks to a little bit of philosophy of science that we mentioned a little while ago, if the purpose of science, if the purpose of ecology is to predict what happens next, the kind of complexity that we're looking at here on this slide tells us that's going to be a pretty tall order. If prediction is not so much what we're interested in, but just, if you like, a more gestalt understanding of what's involved, a more gestalt understanding of what processes give rise to the complexity that we see in predation, if that's the purpose of ecology, then this graph is encouraging, because this graph tells us, well, we know something about many of those arrows and boxes. We've collected data on them. We know a little bit about the relationships. And indeed, we can kind of say something about the gestalt nature of predation through all of the good work that's been done on Isle Royale, in addition to all the other places where predation is studied. So, well, anyways, I think this is a good spot to leave things. This completes part 1 of our mechanisms of predation, and during the next lecture, we'll focus on part 2. So, thank you so much again, as always, for your attention, and we'll look forward to sharing more information with you during the next lecture. Bye now.